I see. So you're not able to speak, huh? Okay. Sure. Why? Maybe there's the options. Okay. Okay. Let's try and see. Let's change the options. Yeah, I think you should be able to unmute. Okay, maybe Adele, can I get started? Guess. Hello, everyone can hear me? Can you hear me? Can you see the slides being presented, being shared? Okay, thank you. Not quite sure what's wrong, why I'm not able to hear any of you, but I think chat is okay. If you need to interrupt me, just interrupt me. So it's great to see all of you again. I think we have some new people joining and some that were part of the original series last year. We had a series of journal club sharing. So thanks for your interest. I'm trying to restart this just to get the conversation and the learning going. And maybe this year onwards, I would need to request a little bit of help from you because I'm sharing some of these sessions, sort of like a voluntary basis. I would need your help from two aspects. Number one, if you look at the chat box, there is a feedback form. So after the end of every session, if you can actually copy the feedback, you can actually submit the feedback form. I really appreciate it very much. And second, I'll be circulating an attendance sheet through Adele. So if you could just help me to sign that. Why do I need that? Actually, I'm trying to maintain, as part of this voluntary sharing, trying to maintain my HRD Corp certification. So your feedback, your attendance will actually be evidence that I'm actually conducting some sharing, some training session. I would need that help from you. So if you continue to find these sessions valuable, if you wouldn't mind to help me with that, I think that would be really lovely. And just for those who are new, the spirit of this session is really more of a journal club, a sharing session, knowledge sharing session. I try to make maybe kickstart it by selecting some papers, going through some concepts, but really it's the free flow of discussion that we are really looking at, trying to build that culture of questioning, of really challenging each other with ideas, with thoughts and all that. So today, the topic actually would be the starting point for continual learning for deep neural networks. Okay, so maybe I'll just get started. All right, it's a bit excited to get started. So continual learning is very, very important problem. And I think this problem actually actually it emerged from industry. In fact, I think we've been getting quite a bit of feedback and requests from COE in Vitrox, to really think carefully about continual learning. And where is this problem arising from? Actually, you see that I guess I've also got some questions. I think Zahan and friends also had written to me after the session January, February, March this year, where you have the problem where, okay, you've trained your deep neural network, right? You've got a lovely high accuracy network and it's working fine and all that. Then 2 months down the road, you deploy in the customer side and then the accuracy sort of just drops. or suddenly you would probably get certain cases where the accuracy is just really low and then it comes back up. So it's this strange situation, not so strange once you go through and you think about the problem, but it's a little bit strange because here you are, there's this promise of deep neural networks where if you collected all your data correctly, right, you've got your diversity, you've got your class balance, you've just made sure you've chosen the right network, if you trained it, you check your validation set, you check your training set, you make sure you have enough validation set, and you're not training on the validation set and all that, and then you've got a really high accuracy, like, yeah, I should perform really well, I should perform robustly, and suddenly it doesn't. So that is the problem of continual learning, and that's a problem that I believe will increasingly become more important as we go, as deep neural networks become more commonplace. And today actually is hopefully the first of several sessions. We're not going to be able to cover this broad topic in just one session today. Today is just setting the seed of the discussion to try to understand where does this problem of continual learning arise from. Actually, I'll argue that continual learning is not the problem. The problem is concept drift. So I repeat that, your problem is concept drift. And continual learning is sort of this umbrella framework which is used to describe a suite of techniques that allow you to handle concept drift. So what is concept drift? So I presume you can see the slides. Let me know if you can't see the slides. Concept drift is this situation where suddenly the figure on the bottom left here, this part. So let me get my pen here. So this part here, this is probably the best depiction of concept drift. Is this situation where you started training your network, right? You started training your network to maybe achieve a particular task, okay? And that task is maybe, well, in this case, is like you're throwing something into a little basket, right? And if you are not accurate, you will miss the basket. But if you train it within enough cases, you will sort of hit the basket all the time. Of course, you are training classification, regression networks. It's not really a basket, it's not a robotic arm, but it's this idea that you're training your network to recognize certain types of images, right? And there's only that type of images, and it knows that, okay, this is an image of maybe an offset error or tombstone error. So you're just training it on that. And concept is a situation suddenly you're presenting your network with maybe images that don't quite look like a tombstone, or the lighting has suddenly totally changed, or maybe the background has totally changed and things like that. So it's like as if the goal, the conditions that you want to detect or classify have totally changed, right? And really the way you sort of can identify this is just really you're looking at your deep neural network was working fine, the accuracy was great, and now suddenly it's poor. Or you will find spotty or poor performance only in certain situations. Sometimes it's poor, sometimes it's really good, and it's very difficult to put a handle on it. Or you'll find that the accuracy fluctuates over time, that kind of thing. So people come up with this idea that concept drift mask is a problem because, over an extended duration of time, when you're running a pre-trained network, when you are doing inference after inference after inference, you find that under certain circumstances, the network just doesn't perform as it normally performs, right? And you might look at the images, you might say, okay, it looks sort of the same, what's different and all that. If it's something very clear, very different, then maybe you can sort of figure it out, go in and retrain. But sometimes it's just not really detectable, right? So that's why this graphic on top here is kind of nice. It's sort of like, things are very predictable. You're able to identify the black class, the purple class, the so blue class, the black class here, and then all of a sudden things start mixing up, and your network is not able to kind of really predict that very well. So this is this general idea of concept drift. The academic community has actually given this a name. So the problem that you're trying to face is really this idea of concept drift. What is a concept? A concept is basically all those features that define a class. So what if we think about okay, so let's let people in. So what do we mean by features that define a class? Well, your deep neural network, the CNNs is learning maybe a certain brightness, a certain sort of spatial feature is associated with maybe a tombstone, or maybe a shift of a component, or maybe a different component size, right? So these are all collectively learned by your neural network as recognizing belonging to features that are associated with a certain class. When these features that characterize that class sort of change And it could change in a subtle way, or it could change in a more significant way. If it's significant, you eyeball the image, you should be able to see a difference, right? Like suddenly the camera is like tilted like 45 degrees. Of course, you see a big change in the image, and probably you might feel that maybe my network's not going to work in this situation because the features would actually look different. What features that define that particular class will look different. So that's what's known as concept drift in a very qualitative fashion, right? It's just that the definition of a class has changed, right? But that is not really a satisfactory concept because it's too fuzzy. And when it's too fuzzy, you can't quite fix it. Because if I tell you the definition of your class has changed, what is your solution? Your solution is find a new definition of the class, which means collect a new data set and retrain the network, right? But obviously that's something that you hope is not what you want to do because it's going to take some time and it's probably not going to make your customer happy and all that. So the question really is concept drift. We are just trying to see, do I really need to throw my network away? How much of that network can I reuse and how do I think about this? So this is where we go for a more detailed, a more rigorous definition of concept drift. So I have no choice. I have to give you some mathematics, but I think your time will be well spent if maybe out of this whole 1 hour plus session, if you can really understand what the mathematics means, maybe how would you actually maybe very crudely kind of estimate this mathematics or probability, then this would be a very good use of the time lah. So we talk about the features over which you are going to be making your decision. That is your image, your raw image pixels. This is called X, and this is called the domain of the data. Sometimes it's called covariates. Basically, it's every pixel value. Yes, Ibrahim, please go ahead. Ask a question.
Yeah. Hi, Dushan. The question is for the last slide.
Yeah.
Does the data drift and the concept drift are synonyms or they are different?
Great, Ibrahim, you're right ahead. Actually, dataset drift is one subset of concept drift. It really depends on who you talk about, but I'm unifying this whole area by just calling it concept drift because what I'll probably be showing you very soon is there's a whole hierarchy of drifts here. Okay, but I don't
I see.
necessarily think it's very fruitful to go in and talk about each and every drift like it was something so new and so special, right? I think you can actually unify that whole framework by understanding it in terms of this joint probability distribution, where you can actually say the drift either happens in the prior probability, P of X, the posterior probability, Py given X, or the joint probability, Py and X joint. So I think in that framework, it's really straightforward to understand concept drift because you can start thinking about the variations in drift because you also have to bring in the time domain effort. That's why we are going to spend some time talking about this probability definition, right? So I think it's kind of artificial to break apart concept drift and data drift and all that like they were distinct things because they're really under an umbrella framework. What is the key idea I want to actually promote to you is really that uh, when you talk about drift, you're talking about changes in the joint probability of the label, Y, and the covariates, your image pixels, X, right? There is a joint distribution, right? In your data, when you're doing inference, there's certain types of pixel values that will co-occur together with a label, and there's a certain probability this will co-occur with the label, all right? And when that probability of co-occurring changes, either maybe your machine, for instance, the light level changes a little bit, or you are looking at a different, maybe a different shape of a different shape of this module, right? Let's say maybe it used to be a 0802 and suddenly there were little wings on the side or something like that. So you would actually encapsulate that or consider that as the covariates, the probability distribution of the features, how do they co-occur with the label would change. So that change is actually what is the underlying source of this need to actually update your system, right? Either your system did not learn all the appropriate probability distributions during training, which is the more likely case, or it actually has changed during your task. So this is the two major umbrella ideas that I believe it's most fruitful to get that. And then when you're going down, yeah, you can call it concept drift. Some people would say concept drift only applies to streaming data, not batch data. If batch data is data set drift, or if the change is in the probability of X, the covariates would appear different, then there's data set drift, So there's slightly different ways to think about this, but I would actually encourage you to think about it as a continuum of concepts. It's not just one or two concepts. And I think there's a little bit of fluidity between how people would define each, but there's been some papers like the Web 2015 paper that really try to put a rigorous definition on things. So pick your source to reference it, but the key idea here is you understand what's happening behind this. What is the origin of this? Okay. I hope that helps, Ibrahim. Okay, let's go back to this problem of concept drift. And I know Pacing, thanks for sharing that. But I'm using the term concept drift very loosely because I don't want to get into arguments that, oh, it only applies to time series data and all that. I'm using it roughly to talk about this change in the joint probability of the covariates and the label. So all your deep neural network systems, when you train them, it is actually solving what you call the maximum likelihood problem. Let's just go ahead since we've talked about that. We will come back. Right. It's implementing this maximum likelihood problem, right? That is, it's making a decision. You give it a bunch of covariates. That means you give it an image, all the pixels, 256 by 256 image, all the pixel values, right? That's that small x here, right? But this small x is actually a vector. It's a vector of all those pixels. And then for each of the possible classes you want to make a decision, right? There's a probability for these given values of x. There's a probability that it belongs to the first class, probability that belongs to the second class, a probability that belongs to the third class, a probability that belongs to the fourth class, right? So the first class may be tombstone, second one class may be missing component, third class may be offset, fourth class may be I don't know, maybe rotated or something like that, right? So if you have a certain brightness, certain features that co-occur in space together, there is a probability that it belongs to each of these classes. And this probability is actually what your deep neural network is learning during the training process. You don't see it, that part is hidden to you. But your deep neural network is basically a probabilistic decision-making system, right? So what it's learning from the data is that a collection of intensity values, either they occur in some kind of spatial pattern or across multiple channels. In the case of color, that's a collection of intensity values. Certain types of values tend to occur more frequently under certain labels. So your deep neural network is actually learning how to make a prediction based on maximizing the probability of this. Okay, so you can think about Py given X, the conditional probability of what the label is given the image. It's a probability distribution, right? There's a probability associated for each class, okay? But, and your neural network is actually learning this, and it's making predictions based on this. Now, your decision can be messed up, okay? Your decision can be messed up in one of three cases, right? So if you look at, if this is your decision can be messed up in one of three cases. That is either this distribution changes, okay, Py given X, this distribution changes, Py and X jointly together, and Px, your distribution changes. Okay, let's go through what each of them means. So the easiest case is actually P of X. That is the probability of the features of your data appearing. Okay, so this is what I think is the simplest example. It's called a data set drift. So when you're going to a site, okay, you're taking pictures of the PCB and all that, there is a certain probability distribution that there'll be a silver pixel, there'll be a red pixel, there'll be a black pixel, there'll be a white pixel. There's a distribution, right? Because, you know, the manufacturer is going to be doing inference on millions of boards, right? So, and then they sort of more or less look the same. There's slight color variations. So there's going to be a distribution on the values, distribution on the neighboring the joint. So it's not just the individual pixel values, but it's the joint pixel values. That if this pixel was bright, this pixel must be bright. If this pixel is dark, this pixel is dark. If the green pixel is this value, the red pixel should also be this value. There's a distribution of values like that, P of X. Now, if the lighting happens to change, or if the angle of the camera happens to change, or you change the lens of the camera, you go from a high numerical aperture to a lower numerical aperture to high numerical aperture. That means you're collecting more light, or the sharpness of the lens changes, it becomes sharper. You will likely change the distribution of the pixels detected in the image, meaning P of X will change. Or if you would change it to a different color, green. So maybe you were training the data with a lot of red and brown components, and suddenly there's a new batch come, there's a new PCB mask, it's all green, it's no longer brown, right? So P of X will change, right? P of X will change. The underlying distribution of the pixels in your data, your inference data, will change. And you have to expect that, right? You cannot just blindly consider that, oh, I've been training with lots of data. Yeah, because when you select your training data set, few things you have to cover. You have to cover the diversity of the data set. That means, does the data set that you're training cover the entire range of all the variations you will see in your application, in your inference? Most of the time, we are sort of so used to training deep neural networks, we get like 1 million data set or 2 million data set or 5 million data set. We're like so happy. We're like, oh, okay, nobody's going to beat me in terms of data set. That's actually incorrect. Sometimes you may actually get 1 million data set, but the question is it varying along the meaningful dimension? That is the dimension of how your data will be in the actual use case, right? So if your data set, you have 1 million data set, all of them are green masks. Actually, to be quite frank, I'm not so hopeful your detection system, your deep neural network will work in the presence of a red mask or orange mask, because he has not seen that variation in the training. He's not learned to basically rule out that variation, or to consider it as part of the feature, right? So when there is a change, P of X, usually sometimes it's called data set drift, it will affect you because most likely in the training uh, time, you didn't actually see a lot of these samples. P of X was pretty low in this case, and suddenly it bumped up, right? So as you can imagine, you have this change in the image properties, right? Under the condition in which you acquire your images. This is P of X, the probability of the pixel values in the image, right? This is the data set drift we're talking about, but we're not talking about just the first component here, P of X, right? This P of X, if it changes, sometimes you will have no degradation in your performance. And sometimes you will have degradation in your performance. So it's not a given that you said data set drift, I will have a change performance. So this is something that to get very clear, right? If there is a change in P of Y given X, then there is going to be a degradation in your performance. If this P of X, that means your data set drift, changes along with the joint probability of Y and X, then it could be that your data set drift doesn't actually result in any noticeable difference in your accuracy in your system, right? So that's why we're just trying to get the terminology accurate, the concepts accurate, right? There are sort of, you can think about it, three general sources where this shift in features, this shift in properties may cause problems to your system. But ultimately, it will cause problem to your system only if it affects the decision rule, meaning that it affects your choice. If you're given these type of features, it affects the probability of it belonging to the first class, the second class, the third class, the fourth class, the fifth class. I'll give you an example. If you have an illumination change, for example, brightness overall, all the images all suddenly become bright. So suddenly there's a shift in the mean value of all your pixels, right? But because all your pixels, whether is a red, green, blue, all shift by the same amount, it actually doesn't affect the sort of decision making, the probability of this set of pixels belonging to the first class, or this set of pixels belonging to the second class, right? Because all of them got shifted the same amount, the probability still retain the same. But you may have a problem, let's say, for example, if you were relying on color features, like you were using maybe your 9-channel colors for your LED, and then, for instance, you have one LED suddenly become bust, the current driver fried or something like that, then there's a higher surge in current, and then the brightness of that green is higher. And then you're relying on that green perhaps to look at reflections or something like that. Then that's an example of data set drift, right? Because the brightness, the darkness, the greenness of the silver color of the the solder will actually appear different, and it would actually change the probability of your decision making because it looks different. The silver doesn't look like a silver anymore. So you're going to be associating a different pixel values to maybe solder underflow or solder overflow. So there's two situations where you can have data set drift, but in one situation, it doesn't affect your decision rule. That means you won't see an accuracy change. In the second situation, it actually affects your decision rule because it changes the relationship between what features are mapped to what class, right? So that's the key point. When there's a change in the probability of the features mapping to a particular class, that's when you have my general way of saying concept drift. You have a problem, your deep neural network is not able to perform as accurate as it used to. All right. Um, are we okay? Do we agree on this, or is there someone who would really like to put up an sort of a different viewpoint? Be happy to hear and have a discussion on this. Okay, never mind. We go on. Stop me if you find that it's a little bit. If you're not able to follow my explanation, or if you don't agree with it, just stop me. Yeah. Okay. So where I'm trying to go with this is again to get you to understand that this idea of concept drift, right? Continual learning is the solution. That's what we want to do because if you understand that concept drifts arises from A, there is a change in the underlying probability distribution of your input data set. That means your pixel images. That's P of X. Or there is a change in how both of them occur. That means maybe it used to be that a tombstone uh, class, right, basically had a lot of shiny parts. And then suddenly in this particular board, the tombstone doesn't have any shiny parts. So this is a change in the joint probability of the label and the pixel. So this is a change in Py of X. Okay, maybe the tombstone itself, the image looks sort of the same as the other flat components, but maybe at some point in one particular board, you actually had a tombstone and it was very shiny. And then all of a sudden for this particular board, it's not shiny anymore. So that's a change of the joint occurrence. That means the network was implicitly relying on shiny pixels occurring together with tombstone, and now they don't occur together. So this is Py of X, this one here. Okay. Or ultimately, the final decision will be the change in Py given X. That is, if I give you this image, these pixels, maybe it's a higher likelihood it becomes rotation. So it could maybe because your, how would that happen? Maybe it could be that one, you might actually have a case of much more rotations or misalignment rather than offsets, right? So when you were training your network, you train with a lot of offsets. Then when you actually run in a particular machine, suddenly you have a lot of rotations. So the rotations are misclassified as offsets because the probability of having that pixels, maybe the component pixels to be at a further spatial distance from the pad, the probability is much higher in this particular data set, but they tend to be associated more with the rotation. So that's Py given X. So these are like sort of three sort of ways that you can say your decision rule is affected because there are changes in your underlying data set on the underlying whole occurrence of the image, what pixels appear when are captured when you have that error. Or sometimes it could just be the frequency of the problem is much higher than it was in the past under your training data set. That's why you're not able to capture it. That's why this problem concept drift is a little bit complicated because there are several origins, several sources of where this could arise. And my hope is that once we understand a bit more how these different probability distributions can lead to concept drift, to lead to misaccuracy or poor accuracy of your network, you can actually pick the correct solution. Of course, when people talk about continual learning, they're saying that the most general solution is your neural network has to continue learning throughout its lifespan. And it's not very I mean, I don't think anyone would seriously argue against that. It's like human beings, right? Like you go to school, right? You go to university, you hope that you should be able to learn everything you need to know for work, right? But of course, we know that that's not possible, right? So you probably have to learn continually throughout your working life, but you're building upon your knowledge of what you learn in university or what you learn in prior job. Sometimes you're correcting that knowledge, sometimes you're adding to that knowledge. So the continual learning paradigm is also similar in its form. And it's easier to accept if you understand from the start that, and you accept from the start that your training data is actually incomplete. Right? If you think about it, most of the time it's because your training data is really incomplete. It doesn't have the full picture, right? It doesn't have the full picture of what your deep neural network will see in every circumstances out in the field, right? Your training data doesn't have that, okay? So it could be it has not covered the full range of different pixel combinations, brightness, darkness, and all that kind of thing. It could be it has not covered a representative balance of occurrences. That means certain errors or certain features tend to occur more frequently in your image data set, your training data set. But maybe in the actual application, they don't occur as frequently, or maybe they occur much more frequently than you have the data, right? So number one, the actual range of brightness, darkness, colors, shapes, features, all they're not really fully present in your training data set. Number two, the sort of probability, how frequent do certain type of classes, certain type of features occur in the training image is not the same as how often it occurs in industry. And number three, the actual, and because of these sort of issues, your incompleteness of your training data set, your deep neural network is just learning a rule, is making certain associations, like these certain features or this certain frequency is most likely belonging to maybe type 1 error or type 2 error, like a tombstone error or offset error or rotation error. But when you go into industry, this may change, right? So this is that idea from where it's coming from, this idea of concept drift. And we want to try to put a little bit more rigor to it. So let me go back to some of the concepts here just to see different forms of it. So here, concept drift is simply the joint probability at this particular instance in time different from the joint probability in a different instance of time. So what I mean by joint probability, we mean the label and the covariates. We mean the class and the image pixels. Okay, the particular instance of image pixels and its class. This is what I mean by the joint probability. So when I talk about instance in time, you can think about it as a particular point when you're making a decision making, right? So let's say your machine is running today, in maybe site A, right? So that represents time T, okay? And another machine could be running at site B 1 week later or 1 month later or 3 months later, right? That is at time U, right? So you can actually think about them as different sites, right? But what we're saying is that the joint distribution at that site A at that particular time and that site B at that particular time U, they're different. So this is the simplest, most general, but very rigorous definition of concept drift. And it's just joint probability has changed, right? So let's take a look at this one. I don't know if I can blow it up a little bit. Okay. Okay. So here, this is trying to actually show you in a graphical form. Just now we were talking about probability distributions and all that. So I'd like to orient you a little bit to be able to read this type of graphs. Okay, so you see there's an x-axis here, it's called x1, and a y-axis here, it's called x2. Okay, and I want you to think about x1 and x2 as being pixel value. So for example, you can think about this as being a 2-pixel image. And there is a third axis coming out of the page. Okay, the third axis coming out of the page is the probability, right? So for a particular value of x1, right? So maybe x1, this one might be pixel value 128. And this one particular value of x2 might be pixel value 20. So if you look at a 2-pixel image with value 128 and 20, there's a certain probability associated with it. Okay, right? Actually, there are two probability values because there are two classes here, there are two probabilities. So the axis coming out of the page is going to be two different probability values. One is the probability of belonging to the circle class. Second is the probability of belonging to the triangle class. Okay, so each of these combination of values, 2-pixel image, has two probabilities: the probability of belonging to the first class, probability of belonging to the second class, probability of belonging to the circle class, probability of belonging to the triangle class, right? So a classifier, your deep neural network, basically has learned all this probability, and it basically is having a decision rule, which is represented by this line here. It's saying that um, all those values, the x1 and x2, these joint values here, the probability of the triangle class is going to be always higher than the probability of the circle class. And in this side, this range of values, probability of the circle class is going to be higher than the probability of the triangle class. But the important point here is for you to be able to visualize. This is basically a 2-pixel image. Each point is basically 2 pixels. Okay, so this point is 2-pixel values. This point is 2-pixel values. This point 2-pixel values. Each 2-pixel values, there is a probability. It belongs to either the circle class or the triangle class. Now, how would you expand this to your typical case? Like your typical images would be maybe 224 by 224 images if you pixels. So you won't have 2 dimensions. You have 224 times 224 dimensions. Very high number of dimensions, very difficult to see. And if you have 10 classes, each of those 224 by 224 dimensions will have 0 to 256 values. Okay, so 0 to 256, so 256 to power of 224 by 224 possible combinations. Each of those combinations will have 10 probability values. Your deep neural network has learned to choose the class with the highest probability value. Okay, and we say that all these dots here, if you look at these dots here, okay, like the circles here, the triangles here, sometimes they tend to cluster closer together, and some places they don't have, right? So for example, the top here, these values here, that there are no dot circles or triangles here. That means you probably won't see images here with 256 by 256 pixels value, or you won't see an image with 0 and 256, right? So these values here, there are no dots here, meaning that it's not probable that you get images there, right? So the probability of X is represented by how dense or how sparse is the number of dots in the XY domain. That's the probability of X. That's the probability of your data set. So when you talk about data set drift, that means P of X drift, suddenly you will get new values, new combination of images appearing here, right? These extra red dots here, right? They're new values, right? Because in your original training data set, there are no values in this region. So the P of X is 0 at this point here, is sparse here. So suddenly you have them here. So if you have them here, then of course, you know, it changes everything. Like it changes the joint probability and all that. But in this case here, this demonstration here is showing you that even though you have a shift in the probability distribution of X, that means you're getting new pixel values that was not in the training data set. There are new pixel values that are appearing in your actual inference, your actual kind of when the machine is working. It's not actually affecting the decision rule. It is not changing the probability of this class given X, right? So you're still in this regime, right? Even though these red values here was never in your original image, but now that they're here, the probability of it being the circle is still higher than the probability of it being the triangle. So you haven't changed the decision rule. Oh, you cannot see my mouse, huh? Okay, thanks for highlighting that. Okay. Can you see this? Okay, pacing. So I'm just saying that, so for here, looking at the top left one here, okay. Do you see my cursor pacing? No, huh? Okay. Okay, this one can see, yeah? Okay, okay. Let me share with the full screen instead of slide. Right, I think let's do that. Okay, let's share the full screen. Okay, we are looking at this part here. Can you see my cursor now? I just have to do a little bit of balancing. Yeah. Okay. Thanks. Okay. Right. Okay, let's go back to here. Okay, so sorry, yeah. So I was talking about this graph here. So I'm trying to get a very good intuitive understanding for everyone. It's time to learn how to read these graphs. Lah. So let me just repeat this, but a little bit quicker. Lah. So this is the x-axis, this is the y-axis. Okay, this is basically representing a 2-pixel image. X1 is the value of the first pixel. X2 is the value of the second pixel. So it's going to be from 0 to 255 here, 0 to 255 here. So every triangle, every circle here represents one possible instance of an image, right? And you will have in your training data set, you can actually plot this out, although it's really crazy for a large dimension. But if you just pick a 2-pixel image, you can plot this out, right? You will see every possible 2-pixel combination will be either a circle or a triangle here. And the reason it's called a circle or a triangle is because in the axis coming out of the image, right, there's going to be 2 probability values associated with each point, right? There's the probability of belonging in the triangle class and the probability of belonging in the circle class, okay? And the reason a point here is drawn as a triangle is because the probability of the triangle class is larger than the probability of the circle class. And the reason that this circle is drawn as a circle is because the probability of the circle class is bigger than the probability of a triangle class. So to repeat, how does this map to your particular images? If you have 256 by 256 image, you have 256 by 256 axis. Each axis has a value from 0 to 255. And then each image represents one point in this 256 by 256 dimension, right? And if you are doing a classifier for 10 classes, each point in this 256 by 256 dimension has 10 probability values. 10 probability values, one for each class. Okay. For regression, it's got continuous lah. For every possible continuous, there's a probability value lah. Uh, uh, but for 10 classes, there are 10 probability values at each point. Okay. So what your deep neural network is learning to choose the class with the largest probability values. So it's learning what we call a decision rule, which is this line here. This line here is an imaginary line, actually. It's something that we conceptually try to draw a line lah, because we are saying that sometimes the network doesn't learn each of these features. It learns a function that is the linear function of this line lah. That's why we draw this line. But really your data set is just basically one point here, 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 one point here. And in the axis coming out of the page, right? This is the plane. The axis coming out of the page is the probability values of the decision. That means there are 2 probability values because there are 2 classes associated with each point. Now here what we're saying is that we're looking at the probability of the data set, P of X. Okay, how do you see P of X? You look at how dense or how sparse are these dots. So in this region, right, this region you can actually say maybe X from 1 to 8 to X to 200, X1, X2 from maybe from 20 to 100. This range, the probability of X, okay, there are 3 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3 out of 10. So the probability of X is 30% within this range. And then if you look at this range here, X1 less than 1 to 8, X2 0 to 255, the probability of X is basically half, right? So this is how you can read it, right? You're looking not at the axis coming out, you're looking at the density of the points here. I can also look at the probability of X of the images that are occurring here. That means X1 that is less than 128, X2 that is greater than 200. There's nothing here. So the probability of me getting an image with X1 less than 128 pixel values and greater than 200 in the second pixel is zero probability for this map. Okay, so you can say that data set drift occurs if there are new images that appear here, these red dots. Remember, each dot is an image. It's a 2-pixel image, right? This dot represents a 2-pixel image. The first pixel value is maybe 100. Second pixel value is 255. This dot here represents a second another image. The first pixel value maybe is 80. The second pixel value is 250, right? That's what it represents. So maybe in the field, when you go, these red dots here, these are additional images that were never present in your training set, right? So they have changed your probability of your data set, right? Because all of a sudden you got new images with new pixel values that occur in parts of the range of pixels that were not in the original training data set. This is data set drift, right? This in its most basic element is data set drift because P of X has changed, right? I have new probability values here. Of course, P of X has changed, right? But of course, the probability changes because, you know, the number of samples is different and all that, but you can calculate the probability, right? But here you look at this, the data set drift did not result in any change in your decision rule. What is my decision rule? I look at this point, I look at the probability of it being a circle, I look at it, the probability of it being a triangle. Not change, it's still a circle. At this point here, it should be a triangle. I look at the probability of it being a triangle. I look at the probability of it being a circle. The probability of it being a triangle is higher, so I still classify this as a triangle. So even though this additional types of images not present in the original training data set. And by not present, I mean you've never seen those groups of pixel values. So pixel values could be color, right? Because you don't just think about this as one pixel value. It's a combination, it's a joint occurrence of pixel values. So joint occurrence of pixel values can encode structure, they can encode color. So there are new structures, there are new colors that appear in the workload in your machines in production. But even though they don't actually appear in your original training data set, because they've not changed your training rule somehow seems to generalize, you have no change in accuracy. You don't actually need continual learning. The world is good, life is good. Okay? But data set drift has occurred. You cannot say data set drift has not occurred because the data set has changed. The probability distribution of the data set has changed. Okay. Now, what will be another an example of a change in the decision rule? As maybe if you go into production, you suddenly get all these extra uh, points, right? Right. You cannot say that they're not there because although they were not exactly detected in your training data set, but yeah, you know, you look around here, there's some density here. So yeah, so they are there. But the problem is these points, although in your original training data set, you had found that the probability of the circle was greater than triangle. But when you go into production, suddenly in some situation, you find that the probability of it being triangle is higher. And this requires you to actually change your decision rule to this one. This is more accurate, right? So this is a situation where the uh, concept drift has occurred. Okay, here, if you think about it, they're saying that the data set distribution actually doesn't change, right? The data set distribution doesn't change, right? Because, and you look at it, how is it I can say the data set distribution doesn't change? Well, maybe because I got more red circle dots here, I got more, sorry, the data set distribution has nothing to do with the class. So it doesn't change because I'm still getting these dots, these red points here. I'm still getting that within the range where I have images here, right? So I have images with this combination of value, but it's just so happened the rule changed, right? The decision rule changed, right? So I have no data set drift here, but the decision rule changed because somehow for those images in the past, if I have maybe x1 equals 50, x2 equals maybe 180 pixel, I would say it's circle. But suddenly in production, I would see x1 equals 50, x2 equals 180. I'll see I have to say it's a triangle, right? So there is no change to the underlying data set distribution. That means I'm still getting images that have the same probability distribution of the pixels. It looks the same, right? It's still within the same region, but the probability y that is coming out of this plane, right? If I'm looking at the probability of a triangle and probability of circle, that's different already. So this is the case where there's a concept drift without a data set drift. Okay. And this is the case where there's both of them. There is a data set drift, like you're getting some data that's out of the range that was in the actual training data set, and that's forcing you to actually change your decision rule because the concept is a little bit different. Okay, so are we okay with these three basic ideas, these three basic concepts, do you follow? Do you get why there could be situations where my underlying data set distribution changes? Sometimes I get a change um, in the accuracy, and sometimes I don't get a change in the accuracy. Sometimes I can get a change in the accuracy, the decision rule changes without any change in the underlying data set distribution, and sometimes I get both. Do you follow that? Just give me a little bit of feedback, either text or verbal feedback or something, because this is the most important point actually.
So the first one on the left is related to the
Sorry, it's a bit
data.
so. Sorry,
Oh,
go
it's a
ahead.
bit soft. Okay,
Sorry.
so the first, yeah, you can hear me now.
Yes, yes, Ibrahim. Yes.
Okay, so the first one on the left is related to the data, the covariance change. The second one is label change. And the third one is a combination of them, right?
Yes.
Okay.
Okay. But Ibrahim, we are not saying that if the data change, there will always not be a change in the decision rule. Sometimes P of X change is enough to change the decision rule. Now you can think about it as you get a bunch of red dots here, and then there's no triangles, right? You know, that can
Mhm.
happen, right? So this doesn't mean that if P of X change, that there's no change in Py of X, all right?
Mhm.
We're just going to the
And this
origin.
is
We're just going to the
which is
origin, how things could change, right? You could have a P of X change, you could have a Py given X change, and you could have a change in both, okay? If sometimes you can have a Py given X change without a change in P of X, it's possible, and then you have a change in both, right? Right. It's just outlining these are the general cases, lah. And all the other cases actually are sort of more special cases of these changes only. You can fine tune them a little bit. This is just going through a bit more changes on that lah. So sometimes they said real drift Py of X is different from Py of X here, right? So for example, uh, I guess this is the original decision rule here. Suddenly the decision rule has changed like that, right? Because of the shift in Py of X, or it could actually be, this could actually arise because the P of X changes, right? So you actually tend to get suddenly more values here where there were none here, right? Or it's the prior probability shift. That means the number of classes Py, that means all of a sudden your in this particular factory, maybe they used to have a lot of, maybe on the whole, when you were doing a training data set, Vitrox machine tends to make more, maybe the place and route machine tends to make more errors on translation rather than rotation. But in this particular factory, for example, for that particular machine, the machine has a systematic error. It tends to make more tombstone error than offset. So that is a prior probability shift, P or Y. That means the probability of the class appearing is different, right? So this is just going through, if you want to just have like a mental exercise, think about all the possible combinations, this is that. But fundamentally what this set of slides showing is just based on this. This is just the key idea. You have P of X shift, P of Y given X shift, or both. That's it. And then you just check whether does it change the decision rule Py given X or not. That's it. Right? That's the key idea. But there are many ways where you can get a Py of given X shift, all right? This is one example. This is your original decision rule. You would see that you probably could get uh, P of X is P of X changes here, or the probability of each of these values suddenly changes, like from the top here, maybe on this portion here, the probability of it being a circle, probability being a triangle is higher than the probability of being a circle. That's why the decision line has to shift there rather than there. Here, this one is both changes lah. This is the case we talked about, which is this one. Your underlying probability, background probability, the P of X changes. So you get additional triangle here where there were no triangles here. And then Py of X also changes. The decision rule also changes. That means not just the landscape on the the X plane change, the plane coming out also change. So to maybe make it a little bit easier, you can think about it as two dimensions of the probability lah. You're looking at how the dots are laid out on this canvas, the X plane, X1, X2, X3. So that's probability of X. And you're looking at how the values of the probability coming out of this plane. That's the Y probability. So there are many actually properties coming out of that, right? One for each class. So and then there's a region-based probability, because that probability of Y might only change in this region, might only change in this region, might not change for the whole thing, right? So there are different variations of this, but they come from the underlying same idea. Like either you're changing the distribution, the density of points in this plane, or you're changing the sort of peaks and troughs coming out of this plane, right? So here, for example, this is, I think they call the Fickle concept drift, right? So this is the decision rule. The decision rule may actually change for just a few values, maybe around the boundary. And this one, the decision rule changes for all of them. And then here, intersected concept drift, maybe they're pairwise flip in the terms of the change. This one, virtual drift, the data set at different time, the distribution will change at different times. And this one, but the decision rule does not change. So in this case, you actually don't really care because the decision rule doesn't change. And this one, the drift is actually local. That means the decision rule only changes within this region of values of X1 and X2, but it's still the same for this one. It only changes for this region, but this is still the same. So these are local changes. And here, this is new features. You see there's a third dimension of data introduced. So there are different ways to conceptualize this. I don't necessarily want to go into too much depth here. I would say that you probably will go into this if you find that this really is the problem in your particular machine or in a particular client side. But in general, when you're just handling a drift, I think it's more helpful to say, is it just a shift in the underlying data set, or has the real decision rule actually changed, right? And I would say that the shift in the underlying data set is probably an easier problem to handle. The shift in the decision rule is really tough, because it actually just meant that your original network had not learned a robust enough decision rule. So there's not enough data and all that. And the third could actually be just like the prior probability shift, which is also means that there are insufficient number of classes and all that. So those kind of situations, either shift in the underlying data set or shift in the probability of the data sets or the classes kind of appearing, that one, you can actually moderate that over time. You think about it, right? Because if you have a proper balance, you keep adding data and all that, at some point you could imagine your network will stabilize and work out fine. The problem, I said that the most difficult problem is actually a shift in the decision rule. That is saying that a certain type of pixels, this range of pixels actually supposed to tell you is this type of error, suddenly it's the other type of error, because you actually hope this is the one that is generalizable. The decision rule for given this type of pixels, this is the class, right? So this I would say this is more difficult to solve, because this actually means that your deep neural network make an error. This one, your deep neural network probably omission. It didn't see some data set. There was some incomplete data set in the past. This one can arise from incomplete data set, but not necessarily so. Okay. Right. So if you are, if you like to really, if you're a taxonomist, you like to actually just check and look at all the different concepts of drift, right? The drift categories, and there are more rigorous definitions. I would argue, because this drift concept is can be very fluffy. Better to find a good definition in terms of like, what does it mean in terms of probability, joint probability for each of these, if you are intending to really handle each and every one of these. But what case that is not covered by these, here all we're talking about is change in the underlying background data, the P of X, and change in the decision rule. The third possible case is actually addition or subtraction of change in concept. Concept evolution or concept deletion. So maybe you had 3 classes, suddenly the concept became 2 classes, or suddenly the concept requires 4 classes. So from this to this, I don't think it's such a big leap. It's just saying the probability of the green the green square becomes 0, right? So you can think about this, every point on this XY plane has 3 probability values coming out of the page: probability of red, probability of, of circle, probability of triangle, probability of square. And then if the concept deletion, that just means that there is a change in the probability of the square. The more difficult one is actually concept evolution. How and when do you know that you have to invent a new probability, a fourth probability, which is the diamond? So this one, hopefully in the future, we might come up with some concepts, but it's not there yet lah. It's not quite clear to me yet how this is being invented lah, right? But from here to here, probably not so big the jump. You can just think about it as zeroing out the probability of the square as opposed to the circles and the triangles. Okay. So I would argue that from a symptom point of view, you will see concept drift when there is you require a change in the decision rule. Okay, so concept drift and all this might happen underlying, but if it doesn't affect your decision rule, you don't care about it because there's no change in the accuracy, right? The underlying problem is suddenly you see a deep neural network, the accuracy change, or rather the accuracy just dropped. So when there is a change, the accuracy drop, this means your decision rule needs to change, which means you need a different algorithm for choosing the correct label from an image, which means you probably have to update your deep neural network, retrain it, change it, something like that, right? But it's clear you need a change in the decision rule because the old decision rule doesn't work anymore, right? Because P of Y given X doesn't work. Second, maybe the situation where you need to introduce a new class or delete a class. So this is, I call it you can think about it as a dimensionality increase for the label Y, increase the dimension of that. I think this is a little bit more challenging. I think this is the one that's probably more widespread that is facing many of you, that you know, the accuracy suddenly changes and you don't know what to do. But here, from our basic understanding of concept drift, we know already we need to expect some kind of training, retraining, relearning, because there's no other way to kind of change the decision rule other than learning something additional, right? Okay, so this is what we've covered just now. The decision rule, what your neural network is doing is actually choosing the label Y. This is called the argument. The label Y that maximizes the probability of that label given X. That means if I give you X, I mean I give you this image, this image with this pixel X1, this pixel X2. This pixel actually has 2 probability values coming out of the page. The probability of the triangle, probability of the circle, right? The decision is choosing whether if the triangle has the higher probability, you choose the triangle. Y here becomes a triangle. If the circle has a high probability, you choose the circle, right? This is the decision rule. So this is just walking you through the statistics for that. And what we like to show now is we want to introduce to you now the time dimension. Just now we're just talking about there being a change in the underlying probability distribution, right? There's a change in P of X, there's a change in Py of given X, or a change in both, right? Change in P of X means this XY plane, some new dots appear somewhere, or suddenly it becomes dense somewhere, right? Py of X means the probability value, you can think about that as the hill coming out of this, the terrain coming out of this surface, right? That terrain suddenly changes, right? So, or both of them change, right? So we're talking about concept drift there, but this change can happen at different points in time. Okay, either different points in time, you can think about it at different instances of inference, right? At different sites, at different points in time, right? So it could be the probability is just holding, suddenly there's a big change. So this is called sudden drift. The change happens suddenly, or gradual, where it oscillates back and forth more and more and more, and suddenly it stabilizes into the new concept. Or it's incremental, it's a gradual shift towards that. Or the worst one, which I think is the most difficult, is actually alternating between the two, right? It is sometimes in this concept, sometimes this concept, right? So here we're not actually changing the definition of concept drift. Concept drift is still a change in the probability distribution, but we are saying that this change you're comparing over different time points. It could be different time points for the same machine. It could be different time points across different machine, or it could be just different machines, same time points. It doesn't really matter. It's up to you to choose your y-axis. But when you say there's a drift, basically you would expect that it's not just something that jumps over here and then it's steady. If it's something that jumps over here, it's steady, then maybe you're in luck. because it's just a sort of a data set drift, maybe very local to the site. You can just tune it and you're done. If it's something like this too, you're fine. But if it's something like this, that's when I think it's most challenging for you, because that means that you cannot just switch your model back to a new model here. You have to retain the old model because your old model performs better at this point than the new model. And you have to know when this switch happens. Right? So generally, if we agree about this definition of drift, it's really the change in the underlying distribution, either the data set distribution or the distribution of the decision rule given the data set. There is a general framework, how people say they can handle this. One is you detect when the drift is happening, and then you adapt to the drift, right? And I would argue that this is the continual learning problem, because the continual learning problem is basically to say, can I adjust my decision rule so that I can handle this case when it arises? That's the continual learning problem. That's basically what you are encountering. Okay. And if you think back about it, what did we say about it? We said, again, the concept drift actually arises from the fact that the data set that you're seeing could change, or the decision rule change, right? And this really arises because your training data set was incomplete. It was insufficient. If your training data set was sufficient, your network would have generalized these cases. So it's because your training data set is insufficient, something has changed in the field, or something new has come in the field that your training data didn't cover. So I do not believe you have a way out of it other than adapting, right? So it's better to just accept that this is actually due to the incompleteness of training data set. We need to have an adaptive network to adapt in the field for that situation. And that's why there is suggested you're looking at a detection problem. That means you first tell that drift has happened, and second, you can start looking at adapting it. And of course, you can start to think about ways of adapting it. Well, the simplest but probably not so attractive way to adapt is you retrain your network. And then the question arises, what is the new data set I have to use and all that? There are other ways. We'll look at it briefly, conceptually today, and then maybe in the future sessions, we'll dive deep to see if any interesting techniques that grow out of this. But some of the brief ways we can say is either you retrain the total network, which just replace the whole thing. Of course, that will work, but that's a problem because a lot of resources take a lot of time. You need a lot of samples, may not always be feasible. Second, you update the network. You change a portion of the network, but the question becomes, what portion do you change? What portion do you keep? What portion we throw away? Third, you can grow the model. That means you have a model for this, you have a model for this, but then the question becomes, if this thing keeps drifting, how many models are you going to store? Right? Are you going to store infinite models? How much space do you have? So that's the question. This is properly the framework of the continual learning problem. That is the problem of identifying when there is a shift in the underlying data set decision rule because of the insufficiency of my training data set, and how am I going to adapt? This is how I'm going to frame the continual learning problem, and everything else will cover that. So I would propose to you, there are really two scenarios now for you to consider for continual learning. One is a permanent drift. I call this permanent drift because once you drifted, you're staying with the new concept, and you could have another drift here, another drift, another drift. You know, the drift, it doesn't need to be two, right? But this is sort of the idea that the decision rule will stay permanent. Once it's shifted, it stay permanent. So a new data, and I would say this is the simpler of the two problems. Why? Because this one, you basically need to update your model. And once you update your model, you're done. You can forget about the old model because you just keep the model that is performing the best currently. This is a simpler problem, right? Because you don't have to remember the past model. And the open question here is really, how fast can you just update it? How fast can you learn and update it? And then do you have any new classes to introduce, that kind of thing? This one, I believe, is the most difficult model because number one, this is a more difficult problem because number one, you first need to verify that actually the drift will actually change back to this concept. Number two, you have the problem of figuring out what is this time frame. Is it 1 day? Is it 1 month? Is it 2 years? Is it 10 years? So if it's 10 years, then what are you going to do? Are you going to use this? Are you going to use this? Right. and how much are you going to change? How much are you going to remember? So I believe this is probably the more difficult, more challenging problem, because here it's actually more important for you to identify when the data change lah, because you need to react quickly. Otherwise, before you can react, it goes back to the original concept, right? Then you just lose these opportunities here, right? So here again, the update rule is you have to update it even faster before it changes back, lah, and the durations matter, lah. And what makes this challenging is you have to decide how much of the historical decision rules you need to stop, right? So just conceptually, we're not even talking about models yet. I'm just laying out to you the complexity, the challenge of the problem. What is the space you're playing in this case? Why? Because my hope is that maybe after today's session, you will stimulate some discussion for you. You go back and think, okay, you see this problem in your application, in your deep neural networks. Is it primarily a P of X drift? Or is it a PY given X drift? Or is it both? How do you prove that? That's the first question. Second, in terms of time, are you seeing a consistent drift, sudden, gradual, incremental, or are you seeing recurrent, where it shifts back and forth? Okay, and then it's up to you to think about this lah. Instead of time, you can actually talk about this as site lah. This could be site A, this could be site B, this could be site C, right? It doesn't actually have to be site time. It's just instances of inference. And there are many, 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 many methods to really organize solution to drift detection and drift detection and how to solve it. We probably will just be quite selective in how we survey this in the future. I will share with you this set of slides. Just keep it confidential to yourself. Huh? Don't reshare it. You can check this up from the papers if you like. But I'd like to actually just take a bigger overview of the problem first, so that once we have this framework, when we discuss the techniques in the future sessions, deep neural network techniques, we are in a position to evaluate, is this really a sustainable, is it really a good idea, or is it just kind of a flavor of the month, very incremental approach, probably not worth spending a lot of time thinking about it, right? So here I want to outline the general possibility of the solution, basically arguing to you why this could be a good approach. If you know when the drift occurs, you know how to update the DNN, right? If you agree with me, right? If you agree with me, just the way I frame the problem with you, I frame the problem with you saying that drift fundamentally arises from your data set is incomplete. Your training data set is not complete, right? If it was complete, you will have example data from all the images your machine, your DNN will see throughout its entire lifetime. You don't have that. You don't even know how the variations in different sites over time will happen. You don't have that. So your training data set is by its construction is incomplete, right? So because it's incomplete, what's happening is your network is looking at unseen cases, unknown cases in the field, right? Is seeing that. So is this question, did the decision rule that your network learned, was it able to generalize enough? If it's not, then you have the situation where you have a concept drift problem, the accuracy is going down. So if you know when the concept drift happens, like, oh, it's starting at this point, then you know that, oh, this data set actually is something that I've not trained my original model on. So maybe I need to collect some data here. I can update my DNN, and then I can fix the problem, right? So that's the first thing. Right? So because of that, I will argue with you, detection of drift is important. This is actually the most important part, because if you can tell me when the drift starts, when the drift stops, I basically can just take that portion of the data and train my model, right? Then my model will be robust, immune to the drift. So the detection part actually will help you. And the secondary optimization is, let's say, is maybe not, is possible, but maybe it's not practical for you to collect all those images on site. Then you're talking about the case of learning or updating your model quickly. So fast learning, transferable learning, few shot learning, this type of techniques is where I would expect a lot of changes, a lot of innovation will be there. So this is why people will pay attention to the drift detection, because once you start to know the drift is a problem, all the images that are being you're doing your inference on those images, all those images become important because they are the ones that your DNN, your deep neural network, has not seen before. They're not trained before, or they don't understand. It's a corner case where it's very important, but it's not handled, right? So you know that once that's happening, that's an important part where your model needs to update itself. You need to start collecting the data at that point, maybe training your model. So detection is important. And second to that, if you can detect, then the question will be, of course, it's going to be better for your network, more competitive if you can find ways to update your model in a quick way, either from those fast learning, few short learning, meta learning, or you can look at the transfer learning type of literature. So these are two general possibilities for a solution, because we are going to be looking at, I would say, the most extreme case, which is the recurring concept. The drift happens and it happens back. So your challenge is, first, you have to detect the drift happens here before the drift ends. Second, once you detect the drift happens here, you have to update the model before the drift ends. Then your solution will be useful. Otherwise, the solution won't be useful. Right? So that's the most challenging case. Okay, so how do you generally detect concept drift? So there are sort of four general ideas to detect. Okay, and we're not going to go into detail today, but we'll see selectively maybe as we go along. If it seems to be important, we might pick some papers out in there. Or if any of you have interest in this, then you can also suggest, and we can have a journal club based on your findings as well. Number one, of course, because we define drift as a change in the probability distribution of the data set. And it's P of X. That means you look at the probability distribution of all the pixels and all that. So of course, you can track the probability distribution of your data set. You can track the probability distribution of your decision rule, P of Y given X, right? So you might say, oh, P of Y given X is quite difficult. How can I detect that? Well, if you think about your classifier, if your output is maybe sigmoid from 0 to 1, and then you're doing a thresholding, that 0 to 1 before the threshold actually can represent a probability value. Or if a softmax, that probability value is actually unified across all the different classes. So before you threshold the class, that value out of your softmax or your sigmoid, tangent here is a little bit more complicated because it's 1 and -1, but you can think about that as a confidence value as well. That actually represents a degree of confidence or probability on that. So that actually represents P of Y given that particular image. So you can actually look at, given a certain set of images from maybe uh, uh, site 1 or machine 1. So you can look at all the values of that logic coming out from that before the threshold, and you can take the statistics on that, right? And if you see a shift in that, this is actually a very crude estimate of change in PY given X, right? Or you can look at differences in X, you look at images across different machines or different time of the day, right? You can look at different ways how you can assemble these statistics. And data distribution, of course, you can look at the distribution of colored pixels, you can look at the distribution of pixel intensity, you can look at, if you're into Markov random fields, you can look at the joint distribution, right? That will give you the structure, 2-pixel joint distribution, 3-pixel joint distribution, those kind of things. So looking at the data set distribution, that's one way to tell when the drift happens. Okay. Second, probably the easiest way to do it, you look at your accuracy rate, your classification accuracy. See, if there's a major shift in that accuracy, there's something happening in the concept drift. Uh, then number 4, accuracy error distribution condition on data environment. This one, okay, sorry. So data distribution was that one, the first, the data set distribution. The performance distribution was the one where you look at accuracy. Contextual based this detection is more of under certain scenarios only you check the concept drift. Maybe you say that I'm only going to look at any concept drift under the situation only tombstone type of errors, or under the situation only from machine A, or only during daytime, or only under operator A's tuning. Someone goes configure the machine, I check that. So that's context-based detection, because you're looking at context-based drift. And multiple hypotheses is that you are doing multiple checks, like it could be data check, performance check, and all that. But what you're just looking for is fundamentally the outcome, the accuracy, and the actual data itself as it changed. So as you know, if you're making this kind of comparison, you will need to identify a batch of data which you will reference. That's your reference data, and a batch of data in which you are evaluating. So what do I mean by a batch of data? You have a set of images, image A, B, C, D, right? So this one you say, okay, this one for sure. This one looks like my desired images. This is my reference. It could be even be your training images and all that. And my new data could be, you know, the sample images I'm taking from my machine at the particular instance in time, right? And you have to decide how many images am I going to test through over what length of time, and then you actually have to find a way to compare them, all right? And then do a significance test. Is it big enough or not big enough? And I'm showing this because it's chicken and egg problem really, right? You know, how much of a data stream, how less of few of a data stream. But it's just to highlight to you the point. For drift detection, you will have to decide what is your reference data, historical data they call it, and what is the data over which you're going to evaluate the drift happening, right? And there's many options like how you're going to select this, whether it's overlapping, whether it's partially overlapping, whether it's not overlapping, whether you are spacing them apart in time, not spacing them apart in time, are they sliding, are they not sliding, different ways to do it. But I would say this is the framework. You will expect to have some kind of reference data and some kind of evaluation data. And what makes this challenging is you have to decide how few samples you're going to make the decision on and how fast you're going to decide the drift, whether when the drift happens. So this is in the extreme cases, but this is the framework for drift detection. You cannot run away from it. There'll be some granularity there. Okay, finally, maybe just as a kind of exercise in thinking, if you want to start characterizing, does your deep neural network, does your data actually have drift? How bad is your problem, right? Because the first step is to just diagnose your problem. How bad is your problem when you talk about drift before you start thinking about the solutions, right? You can talk about the magnitude of the drift. That means you're finding a measure of difference between the probability distribution, the duration, how far apart they are in time, the rate. This is a little bit tricky because it means how fast does the drift generally occur in time. So they're looking at the path length. The path length is actually a kind of weird metric where you're looking at um, how far apart are the drifts in general between every two components of drift, and then the average of that is the rate. That means how frequently is drift occurring in your system. And then there's also the start time of the drift and the end time of the drift. This is called the drift scope. That means within one batch, right? So this will be the start time, this will be the end time. So this is the start time, this is the end time. So this is one drift scope, this is one drift scope. So this is just some concepts throwing out that could be helpful to understand the severity of your drift. Okay, but the thing is, it's still an active area of research. People don't really have a good measure of distance in probability distribution. You'll be quite surprised. It's quite difficult to measure difference in probability distribution. I think just from the papers, we propose 3 possible metrics. You can take the KL divergence, really very familiar to people who have gone through the generative adversarial network models. This one can be computed for discrete data set. The Hellinger distance, which actually you're looking at the probability distribution, the discrete probability distribution at each class. You take the probability distribution, the square root of that, you calculate this, or something called the total variation distance, which is something like this. It's a difference between the probability distribution at each point, but it's a sigmoid. It's expressed as a standard deviation. Okay, so 3 of these is possible. Okay, so we are not going to go into, again, a lot of details here, but if this is interesting, people think they want to try to apply it, maybe in future, Jacob, you can write me an email, we can start to dive a little bit deep. How do we calculate this? Some practical ways to calculate this and see what happens in your data set. But you will have to prepare a reference data set, a data set under evaluation, and to figure out what kind of strategy you want to batch or group your data across. All right, and then you have to choose one of these measures of probability distribution in order to put a number on the severity and the duration and the time. Okay, let's say you can detect when the drift happens. How do you fix it? I think just also from a general top-down approach, there's probably just going to be all kinds of variations only on these three general ideas. Number one, you replace the model. Just throw away the old model, create a new model. And this works well for drift cases like this. Plus, it just makes sense. So why would you want to remember an old scope when the new scope is persistent, right? So the first option you have is retrain, replace the old model. The second option you have is you keep adding models. And then this is represented by what they call the ensembling method. So you know, in one of the very cheap, easy tricks in machine learning is you can build a classifier. You build many different classifiers for the same problem, and you combine them all in an ensemble. Right, and this is a very easy way to get high accuracy, even if your individual classifiers are not doing so well. I think this is called boosting, right? So it's been shown, the earlier works on ADA boost is shown that even your classifier individually doesn't perform so good. When you have many different classifiers and you combine all of them to make a decision making, you can get high accuracy. So it's this idea that maybe you start with one deep neural network model for the first scope. Then when you have a second scope, you train another deep neural network model. You combine the two models. They're two separate models, but you can add maybe a final layer or final two or three decision layers so that they are ensemble, they become a joint classifier. Then every time you change drift scope, you add a new model, you add a new model, you add a new model. So you just keep adding models, and each of these models is very accurate, fine-tuned accurate for a particular drift scope. And that will allow you over time to be able to handle all these cases, because it's like saying that uh, one way I like to relate deep neural networks is to an organization. So let's say if you're an organization, if you're used to solving electronic problems, so you have one electronics engineer, specialist to repair. Suddenly someone brings to you a mechanical engineering problem, mechanical problem. So there's a drift, concept drift problem, right? So what you do is you train a new mechanical engineer. So you add a mechanical engineer with your electronic engineer. So you have one electronic engineer and mechanical engineer. So in future, you can handle both electronic and mechanical problem. Then later on, suddenly come one logistic problem, right? So you train a logistic person, right? You add three, right? So then you group all of them, they work together, so they're an ensemble. Whereas the replace model is when you have an electronic problem, you have an electronic engineer, then suddenly you get a mechanical problem, you throw away you fire the electronic engineer, you replace with the mechanical engineer, right? The third approach is called the update approach. And some of the old papers view this as you're adding or maybe modifying some elements of the ensemble, but I would say this one is a bit more general. There are more general ways we can think about update model. How does update model differ from add model? Update model really, I think the key idea here is that you are sort of maintaining the number of resources you use to manage the model. There is a reallocation of resources. That means the old model, you have to reduce the resources, in this case, the number of weights, the number of connections. And the new model, you have to give some resources, right? So there's sort of in between. You are not entirely getting rid of the old model. You're not replacing with the new model. You are reducing the size of the old model here, this part here. And you're still adding a new model, but you're adding it not by adding additional resources. You are using some of the released resources to add a new model. This is the update model. And I think all of us will see that going forward, really the update model is the way to go. Because as I throw out to you, you don't know how many concept drift conditions or drift scopes you will actually see in your lifetime. You don't know the duration of all of that. So if you're preparing for the worst case, the question is how much resources are you going to allocate in order to solve this drift problem? So if you would take a example from human learning, human learning is, we learn skills as we go, right? And when we are learning new things, we can keep adding new skills. But the way we add new skills is not by growing our brain. I mean, when we're a kid, our brains will grow up to a certain point, but when we're adult, our brain is a fixed size. So there's only a fixed constraint in terms of resources. What happens is we become more efficient at doing the old tasks. That means we will have to use less resources to encode the old model, and we will have to find a way to integrate the new knowledge into our model, right? And what happens is sometimes when we use less resources to encode the old model, we tend to lose accuracy. We start to lose accuracy on the old model. And at some point, if we really don't use the old model, we will lose it altogether. So it's the case that sometimes some of the skills you've learned, you could become very good at it, and then suddenly you become very bad at it, but you can still do it. Or in some case, you totally forgot how to do it already, right? So this is kind of that model that I think will make sense to most of us as a stable and sustainable model moving forward. Unless you have unlimited resources and you want to track things, then maybe the adding model would be the way ahead. The replace model, of course, would be the way to go. It's probably the simplest way if you know that your drift is permanent. Okay, so just refreshing you, because this is why I argue this problem is the easiest. This problem is actually the tougher one. So my conclusion really, starting this problem, looking at continual learning. How do you do continual learning now that we have defined concept drift? I believe model update is the only sustainable way forward, because it is the only framework that will handle both scenarios of drift, right? So this is the replace model. This is the replace model. This is probably the add model, but add model is not sustainable. So the update model can balance learning a new concept and retain old concept, but the keyword here is balance, right? Because the new concept will require additional resources. You got finite resources, meaning finite compute power, finite storage, finite time to compute. So you cannot expand your models indefinitely. One good way to do it is really you must find a better way. I think the networks that the continual learning solutions that will work would be the old concepts must be forced to be more efficiently represented, meaning fewer weights, fewer layers, this kind of things, use less resources. And at that point, you also have to accept a degradation in the quality of the old concept. And then there's a balance, how much old, how much new. And there needs to be some kind of rule to determine how to allocate the resources to all concepts. And also, sometimes you can think if you're able to do it synergistically, you actually can take the new concept, the old concept, and find a more efficient representation to represent them together. But this is difficult. I'm not quite sure deep neural network still has a way forward, but I think some of this interesting work like generative replay and all that is moving into that domain. Okay, so this is just an ending slide to share with you. Google thinks of everything. This is really the framework that we're looking at, progress and compress. They call it progress and compress. Progress is the update state, learning the new concept. Compress is the model reduction state, where you are actually finding a more efficient way to allocate that to represent the known concepts, the known network, right? So is what they're proposing is alternating between progress, compress, and this is how human brains work. So I believe this framework will be the way forward. But what I may not agree is I may not agree with the method they use for compressing. They're using the elastic weight compress, right? I mean, there are many different ways to do compression, right? You can do pruning, you can do transfer learning from large network to small network. You can do generative learning. So different ways is really an open task in research to really identify the most efficient way to actually compress a network, because it goes down to the question of what is the optimal size of a deep neural network. You're asking that question when you're talking about compressing, and it's still an unknown question. What is the optimal size of a deep neural network? So that's where I think a lot of the innovation will be, and the progress will also be just variations. Probably it might move along the line where we're looking at how quickly can networks learn. How quickly can networks learn, maybe with a transfer approach, right? You basically start maybe with a transfer learning of your compressed network, or transfer learning with a scale up version with some additional resources to learn new concepts or to modify the concepts, that kind of thing. Okay, so conceptually, concept drift and complex learning, continual learning is a problem. It's a problem of incomplete training data set. Because if I argue to you, if your training data set is complete, you will not have concept drift, because you'll be able to see every possible probability and every possible situation in the real data, right? But your training data set is incomplete because you do not know how this data set will change over time in the real world and things like that. So you are only discovering parts of the training data set over time. So over time, you're receiving the full picture of the data set. Okay, so the real question is really how much information do you require and how quickly can you adapt? So how much information require? Of course, those networks that can just train and update their concept with only a few samples will be much better, much more agile than those that need many, many more samples, like the full network retraining and the speed. So fundamentally, I believe the network must adapt. Continually, continual learning is a question of adapting your network. The question is how you're going to balance the resources. All right. Okay, I'm going to stop here for today. Maybe to take any questions, if any, or if there's something that we can discuss a little bit further, then maybe I'll look for a new set of papers diving deep into some of these techniques for our next session, if there's interest. Yeah. Okay. So any questions from anyone? Any comments, any feedback, any sharing?
Uh, so in the slide just now, you show the ensemble model. Can you go back to the slide? Yep. So add model number 2. So let's say we do add module on the to combat the drifting, right? When the model kind of don't agree. Okay, how should we find a consensus between different model?
Ah, okay. I'm going to just reason out like this lah, Yongka. I'm not 100% sure of this yet. Thoughts are still evolving lah. So if you think about ensemble models lah, right? I can train the history of ensemble models is same data set. Maybe I just train 5 different models lah. I train 5 different models and then I just group them together by some classification layer lah. And the reason ensemble works is because some models will, at a certain part of the data lah, let's say classifying tombstone, model A will be fantastic, model B will suck, model C, D, E will be quite good. Then maybe when classifying offset, model A will suck, model B will be fantastic, model C, D, E will be quite good. So the ensembling process is taking into account all of these by weighting the decision. It's just saying that something like, if I see this kind of situation, I'm going to pay attention to the electronic engineer and the mechanical engineer. If I see a robotics problem, I pay attention to electronics and mechanical engineer. If I see a customer like data problem, I pay attention to the logistic and electronic engineer. If I get machine breakdown, I pay attention to the mechanical engineer. So it's applying a weight to the model. That's what the ensemble is actually doing. So I don't fundamentally see a conflict between those models that are ensemble, because the very definition of an ensembling is you allow each model in the ensemble to have its own opinion. Some of this opinion must be aligned, and some of this opinion is allowed to be contradictory. As long as maybe the majority of models have a sort of similar opinion, I don't think your ensemble will go too far wrong lah, right? You only have a problem lah in the ensembling when maybe you have too few models and they are really contradicting in all situation. Then I think your performance will just drop lah, for example. But in general, when you have most models, if most models or ensembles are weakly supporting one view, and then there are a few very strong, and then there are a few that are opposing, I think your ensemble usually can learn, can be trained to pick the correct solution. Because what the ensemble, that final decision layer, is learning is just who to pay attention to for a particular class of data. So to me, if you're just taking an ensemble approach, the conflict part doesn't quite arise because you're relying on the ensemble. That means your final decision layer. I like to think about it as the management layer. The management layer is changing. So you're changing the management layer. The expertise is still in the company. The engineers are still there. You're just adding engineers. It's just how you want to reweight the management layer in terms of making the decision only. So even if you were to make a mistake, I presume you should be able to recover quite fast because your management layer is quite quick, you see.
Right.
Is that convincing for you, Yongka?
I guess it's down to the implementation details because
Yeah.
it's down to the implementation details. So and another question is, uh, for our deployment, right? I guess the user who have done the production deployment will need to correct me on this one. In the production, we actually never. Okay, I actually never monitor. I actually never see a data drift uh, in our production anyway. So what do we have is customer complain to us that, well, you have some misclassification. So it is unknown to at least me that this is because of the model is just, well, not trained on the not trained on the complete data set, or data drift is really happening. So how is there a data set, or is there a way for us to verify that, let's say we implemented a drift detection algorithm, how do we verify that our implementation is actually correct? So let's not talk about how do we do this monitoring in production, because collecting the information back from customer is slightly difficult. But do you have a framework for us to test how can we, detect that a drift is happening?
Okay, Ilka, I suggest this as a possible framework lah. There are few quick things you need to test first lah. Okay, so now we are at this balance between concept drift and overfitting to a customer. That's what I'm seeing lah. Because you said in general, accuracy doesn't really change. It's just your customer is trying to push the envelope, and they try to push the envelope, they try to add certain extra training, and then the model breaks and these kind of things lah. So it's just a question about improving the accuracy of the model lah. But your model, you're not actually seeing a drop in accuracy and this kind of thing. So I would actually argue you should check whether is it overfitting issue or concept drift. The reason I mention is like this, right? Because you train on a broad class of problems, and your model is actually meant to serve as many customers as possible. But when you push it into a production floor, you probably want to tune your model to overfit more towards the customer's scenario. No, but the danger is when you overfit there, maybe it will break the generalization. That is a danger lah. Right? So the first test I'll actually run lah, if you have this example data where it break, maybe you try to retrain your big model, transfer learning, and then you just try to retrain and then see that if you retrain, where does it break lah? If you have a case where you have these few extra classes that misclassify, then when you retrain it, wow, this one works, but then you have to give up some accuracy somewhere else. Then you're playing this back and forth game. Then my argument is you're actually at the balance of you are forced to overfit, and your model loses the generalization ability lah. So in this case, I think it's something that we explored or talked about very, very early on lah. I actually think it's better for you to have a smaller model. Maybe you can do a transfer learning on this or something where you just train this smaller model or more compressed model specifically for customer side, and maybe you ensemble the two lah. That's where I'm looking at lah. Because the idea is something like what we are seeing is that the over training on those few samples will break your general model, will kill your accuracy in some other domain and all that. You don't want to do that, because if you do that, then you lose business. You cannot cover the broad case. But for these particular customers, they need a way to bump their accuracy up. Only for this particular. So it's sort of like you have your base model, but there has to be another tweakable model where it can be more flexible lah. That model maybe you can let it overfit a little bit more and things like that on special cases, and then maybe you can just train this model, and then there are interesting ways you can think about ensembling them lah. Of course, one way to look at it would be if it's a clear-cut case lah. Number one, let's say you find that if you look at the logics lah, is like very close to the threshold value and all that kind of stuff. if you can identify that particular few outliers data samples is occurring at the borderline of all the logics, then you can actually have a no decision zone, where in this decision zone you actually transfer the decision making to that model or something else lah, right? So you can do that, that newer model, and then you can let the decision making do that. I would be quite interested to explore if we were just to train your existing full-length classifier, you use transfer learning to try to train it in a generative fashion. So you can use a generative discriminator to say, is this within that scope of data or outside the scope of data? So outside the scope of data, you transfer to the specific or the special purpose model. So I'm thinking it's more of an issue of capacity overfitting rather than concept drift here. And the reason I argue this is because it's like you want to include this concept. Yes, you can tweak your model to move over here, but you tweak the model, move over here, this model doesn't perform as well on the other concepts. Then you took it back, it doesn't perform here. So it's like you're being forced to choose between the two. So that one, it goes back to probably fundamental feature representation. I'm not so sure why it gets stuck in that minima. It might be you might have to roll back and then train it better or something like that. I mean, this is not if you want to find a more stable and permanent shift lah. But the problem with this is you actually don't know if that's the case. So for this particular case, if the quick test lah, I said, if you retrain the model with these additional images and then you do worse on other images that you used to do well on, but if you find it's a back and forth, then I would actually say it's more of an overfitting problem rather than a concept drift problem. Because I believe the concept drift is a bigger shift. It's more of like, it warrants a bigger shift. It's more like if there's the rule just sort of breaks down and you're really not achieving that high accuracy. But if you're talking about just very sparse samples, maybe 1 out of 1 million, 1 out of 10,000, that kind of things that customer just not happy, want to push the envelope. I still think it's better for you to have a two-stage process, a filtering process. So you don't break your first model, but you have a second, more special purpose model to solve that case. And that special purpose model can be very overfitted to customer requirement. Or it could even be so overfitted to that particular board model and all that kind of things. Because my argument is, normally you want to optimize the common case. So it doesn't make sense for you to spend a lot of energy, money, resource to optimize for very, very few poor cases. So if these are outlier cases, it's actually better you just start something else, another parallel network, second one, just to do the evaluation on that. But I think what you're sort of hinting is, if you actually want to roll it back into your main network, that means you're trying to find a better or general purpose network. In that case, you have to find a method to actually collect all these samples to enhance your training data set. And I'm not entirely sure transfer learning will be able to fix that. Why? Because the idea is something like this. Like your network is already there, and then if you're training on these outliers and then you're just kind of shifting the accuracy, is big good on this, bad on the other class, and you shift it back and forth, it means your network is sort of stuck there. It's not likely to be able to get a generalized feature representation. So you actually have to start at an earlier stage of your network weights for it to learn a new topology or connection. I don't know, did that make sense?
So the main problem is we cannot simulate this scenario. First, we don't know if the data drift ever happened in Vitrox. What we have is accuracy drop. I'm sorry, not accuracy drop, but rather customer feedback that we misclassified a few image. We don't know what's the performance over the time. Maybe the performance is actually still good. It's not definitely not 100%, but actually still good. Just that the customer found some misclassification and then they, notify us, and we thought, oh yeah, the model degraded. That may not be true. Of course, this need to go back to the people who already deployed model on production side, if this is true. So the motivation of us wanting to do continual learning is really how can we deal with those few misclassification data without having to trigger, retraining. So one of the way you have mentioned just now, maybe just do an example, just maybe do a transfer learning on a few images, and then somehow combine the result between two and yeah, uh, just deploy it. Uh, what I'm looking for is, let's say data drift do happen. How can how to simulate this kind of situation? I mean, in the experiment, how does other peoples do this? How do they know? Sorry, how do they simulate that this is when drift happen, and after they do some whatever they training, and they're able to get back the good accuracy? Because I don't know how to simulate this, and then if I don't know how to simulate, I cannot do anything about it.
Right, right. So we have a good start today. We define what is the change. First thing we can do is we can look at some open source data sets that has contained all of these examples lah. Of course, they're not going to be relevant to PCB detection and all that lah. How does data set drift happen and how to simulate that? I mean, if you talk about simulating, possibly you can go back to the initial idea some years ago. We talked about synthesizing images and all that. That's not really the real issue lah. That's just hard work and getting it done. My real issue is I think you're trying to solve a customer problem. I think the customer problem is not so well defined. So we run the risk of actually putting a lot of work in a problem that's not really a problem lah. That is my worry lah. Want to simulate. Okay, but the customer is able to give you those images that perform very poorly, right? That one you can obtain, right? Not a problem, right?
We don't know if the model performed poorly. Okay, this is obviously on us because like we didn't do enough monitoring on our model. What we receive from the customer mostly will be our model misclassified a few images, and it is actually unknown for us that is the performance still good, just that we misclassify some. This is actually bound to happen.
Okay.
Or the performance is actually degrading so much that the customers start to notice some misclassification. So the point is that I do not have a situation I can definitely tell you that data drift happened. So without this kind of environment, I cannot write or test an algorithm on it because I don't have the data for it.
And well, I would argue that's the first thing you can start to do. Basically, as I mentioned, your classifier, there's a bunch of logits, right? And then you're thresholding your logits, right? So if you were to just look at the collection of logit values lah, which we would take as the probability of it being in that class lah. Later, if it's tangent and hyperbolic, you can fix that lah. But assume it's sigmoidal, you can take it as a probability. So what I'm proposing is actually before you launch a model, you have your golden networks at Vitrox and all that, right? So you've got your training data set, you've got your validation data set. Do some simple statistics. You put in all the data within one class, second class, third class, and then you look at the distribution of the logits, the joint distribution lah. Okay, for this class, this is the range of probabilities I will get, right? You'll be able to plot the distribution of the logits lah by class. So you by different images lah, you just plot that lah, right? Right, then your customer side, if you can look at the logits, that will actually tell you whether there is a shift lah, because you have the distribution, the probability distribution of all the classes response to one type of image, right? So you know Py given X. That's what you know, right? That's the logit value. That's what I'm proposing. So you said, let's say I have 20 images of class 1. Good. So this is the range of my logics. It should be in this range, lah. Okay, so if you see a shift in that range of that distribution, that should be enough to trigger something already, lah. I would say that would be I'm not sure it's straightforward, lah, because I understand it's quite difficult to roll things out on customer side, lah, but it is actually a sort of code that maybe you can write and deploy internally on your network, lah, because what you do is just collecting statistics internally on the distribution of that only, right? And then you're just looking like, say, within a day, within a week, within a month, maybe you have to just look at a suitable duration for that, lah. Maybe a bit of experimentation, whether there is a significant shift in that only or not. Yes or no? That only. So that would be actually be you maybe you might not need to go to find P of X, lah, whether there's a data set drift. But what we're saying is that if you can see that there's a shift in PY given X, lah, something is happening somewhere. Either the rule is not updated or something, but there is a shift, lah, right? Because for a given, because what the customer will say is it's supposed to be this class, ma. It's supposed to be performing well, ma. But you already recorded these logic values, you will be able to check whether it falls within this distribution or not, ma.
Yeah, so what you mentioned is more like error analysis, so kind of figure out why the model failed to predict.
It's not even why yet. You're figuring out where the model fails. Where? Which class?
Okay.
Is it local? Is it global? Is it one particular class? Is it one set of images? Because, for instance, you get PY given X. That means I'm looking at the range of all the 10 classes, the probability that I'm giving you type 1 images. Let's say it's supposed to pass. See that? Then I give you type 2 images, tombstone images. If I see, for example, the tombstone images, suddenly the probability of class 1 tombstone drops and the probability of other classes go up, then I'm like, it's probably something weird happening. The total distribution looking like rotation, something like that. Or if I say like the normal one, the good images, suddenly I see the probability sort of shrink towards, all of them shrink towards the threshold. They're not really very high probability, low probability. That means there's something general in the images that's just confounding all of these. Like it's this idea that from this, maybe you get a little bit of a hint, lah. The image looks a bit more like which kind, lah. Right? Because you probably will have a distribution. You said this set of images will look like rotation or that kind of thing. So then you can even do a more interesting data map that is your own training data set. You can actually look at the outliers. Look like for normal images, it range from this type of distribution. These are the extremes of the joint distribution. This is what the images look like. Look. So you can start studying also what is the feature representation decision rule of your model from that, lah, with a visual example, lah. But you are taking it by looking directly at the logics, which is the joint PY given X. It's like a pattern matching, lah. So you see a shift in the pattern, you know it shifts more into what. Then you can start looking at more interesting things like, is it possible for you to make PY of X into a metric space? If you can make it into a metric space, you can throw metric learning to your classification, then even better, lah. Just saying that the 10 concepts, you are just kind of aligning which of the two, which of that is more better, lah. That's one concept or one framework I have very crudely at the moment, lah. But I think probably more can be done looking at PY given X. P of X, of course, I think is quite challenging. There are some tools that Google give. Haven't explored yet the what if tool and all that. Starting to look into it a little bit. There's some data exploration tools that Google already have. Maybe that could also be a starting point to see if from Vitrox side you want to look a bit more seriously at that. But yeah, I'm not sure it's really a concept-driven problem per se, but if you want to start something, maybe my thought will be just more like a model augmentation, lah. Like you have a second model that is overriding the first model under specific cases, lah. But to do that model augmentation, you must have some kind of scenario where you know that the first model is not performing well in this situation. Okay. So from that, that's sort of the thought that maybe if you want to train that way, you can actually train it based on the logics rather than the decision, right? Because when the logics become like not really very strong, not really very highly confident, right? Then the decision becomes more heavily weighted to the new sparse model, lah. So that's sort of that idea there, lah. Of course, your sparse model you can initialize it with the same weights, but you allow that sparse model, that model to evolve radically lah. But you allow two-party decision making, one versus the other, or if you want, you can also allow three-party lah, but that one have to think a little bit more lah. But I think you can just do a two-party lah. There is one is like a on-site specialist, and one is like a generalist looking at all of Vitrox experience. So that will be something I would say probably a bit more tractable to try lah.
Right.
Yeah, because then if the customer not really like it, they can always retrain very fast and then your second model actually doesn't need to be deep
Yeah.
because you can have feature sharing also. You can
Right.
CNN layers or feature sharing and go for those kind of things lah.
Yeah. Right.
Hmm.
Okay.
Okay, right, great. Any more sharing, questions, comments? All right. If not, then if I can just briefly request lah, I need your help. Can you please fill up the feedback form? I have a feedback form here. I put the link here. If you wouldn't mind to just fill up this feedback form, just help me out here. Just give me some brief feedback on that. And if I'll circulate an attendance list, if you can just put a digital signature on it, that would be just really great lah. And then if you're interested for future sessions, then just let Adele know. I'll put together another set of paper. We look for another date in the coming weeks or months lah. All right. Okay, so thanks everyone, and if no final questions, then we can call it an evening. Needs 5 Microsoft account login. Okay, let me quickly see if I can change the. Okay, sorry. All right, can you please try again? Sorry, yeah. Got to. Maybe I'll just share the attendance sheet as well. Then maybe don't need to trouble Adele to circulate it.
The link can use now, so should be good.
Link can use,
Yeah.
Okay. Okay. And maybe this is just the attendance sheet. If you just put some kind of signature, it would be great lah. Okay. Yeah. Right. Then in that case, I wouldn't want to keep all of you. So thanks again, and just work with Adele to see if there's interest for another session. We'll look into some more detailed techniques lah.
All right. Thank you, Dr.
All right. Okay. Take care.
Thanks, everyone. Take care too.